common inquiry into our technical department is relating to the use of our Quinn Lite blocks below DPC and the requirement for tanking the blocks in a bitumus type substance for the use in this application. I'd first like to point out that Quinn Lite have full third-party certification for use below DPC, so all the relevant freeze-thaw tests etc. have been carried out and there's no issues with structural performance when using the blocks in this application. We'd also point out, however, that to get the best thermal performance of the blocks, they should be kept dry. But there should be no requirement in most instances to tank the blocks in bitumen to achieve this. So here we're going to look at two typical details to see how we can keep these blocks dry quite easily. So the first detail here, we have insulation below a slab. So we have a 150 concrete slab here. Our insulation below this, I've chosen insulation thickness of 175. It's always good practice for your insulation thickness to coincide with blockwork coarsening. So here we have a soap bar 100mm deep and a standard block which is 225mm deep, making an overall depth of 325. So if our subfloor and our insulation equates to 325, it makes life easier on site. In some instances we may say 175's too thick for insulation, is achieving U values well in excess of what we need. However, we can look at alternative lower performing insulations. For example, here we could use EPS, Pearl, which is a grey EPS, or even ordinary white EPS to achieve the U values we require. Here I've shown partial fill cavity wall insulation. We have a concrete block inner and outer leaf. However, the inside leaf could alternatively be a timber frame. Our radon barrier here is underneath the insulation, goes up over this block, out and down. With a DPC and the inner and outer leaf typically needs to be a minimum of 150 above ground level, and I've shown the DPC sealed with the radon barrier at this location, which is good practice. Here, as you can see highlighted in green, this is where the wall insulation and the floor insulation are broken. So here we have introduced the Quinn Lite block. We have a free draining cavity below the insulation and we have a perforated drainage channel out here. So any water running down the inside of this block freely drains out and away from the structure. This is good practice in all building to have proper drainage around your building. So if we look at this particular block here, it's protected from moisture by the radon barrier. So the only way this block can get wet is through rising damp from this block beneath. So to keep that block dry, we can simply introduce a DPC at this location, and you can let that on out underneath your radon barrier as necessary. So now we have a Quinn Lite block here which is fully protected from moisture and it will be dry in all instances. And here in this detail there's no requirement for tanking or dipping the blocks in bitumen. So we look now at a second common floor construction. So here we have insulation above the slab. So we have our concrete subfloor here, we have our insulation and our screed. Here I've shown 75mm of screed and 150mm of insulation, which adds up to 225, which again coincides with blockwork coarsening. The wall construction is the same as above. Again, this could easily be a timber frame in our leaf, and again we have the free draining cavity here to allow any water running down the cavity to drain off. Insulation should not be sitting in water, so it's important that that insulation, the cavity, is fully drained below the insulation. So again here you can see the DPM or the radon barrier running out up over this block, down and out. So already you can see that the Quinn Lite block in this detail is already protected from rising damp, so there's no requirement for any additional DPC in this construction. Again, we have our DPC and the inner leaf out, down and sealed to the radon barrier, which again is good practice. So as we can see again here, there's no requirement for the use of any sort of bituminous type products to coat or dip the blocks to keep them dry. That block is dry in that application, and it achieves its best thermal performance. So we've looked at two situations where our Quinn Lite blocks can easily be kept dry at that critical floor to wall junction. We're going to look now at what happens to the Quinn Lite blocks if they are subject to moisture. It has been brought to our attention that on some situations the detail hasn't been done correctly and the block may be subject to rise and damp. So we've done some in-house testing to see how moisture will affect the thermal performance of the blocks. So if we look at our typical Quinn Lite B7 block, the thermal performance of that block in its dry state is 0.19 watts per meter Kelvin. What we've done with that block then, we submerged that block in water for 48 hours, then took the block out of the water and tested it straight away. So the block was at full saturation, and the test result revealed that the thermal conductivity of that block at full saturation was 0.33 watts per meter Kelvin. And if we look at this detail here, even if that DPC wasn't in there, which is an incorrect detail, but if it wasn't there, the block is only subject to rise and damp, so that block will never get close to full saturation. So these figures here are based on full saturation, which really is worst case. We look then at our Quinn Lite B3. The dry conductivity of that block is 0.12 watts per meter Kelvin. The fully saturated conductivity tested at 0.29 watts per meter Kelvin. The interesting thing about this particular figure here is, if we look at another common thermal block which has now been used throughout Ireland, the lightweight aggregate block, the thermal conductivity of that block in its dry state is 0.33 watts per meter Kelvin. So even if the detail is not done correctly, like we've shown earlier on, the thermal performance of our block in its fully saturated state, which is absolute worst case, is still on a par with a dry lightweight aggregate block. So what we must ask ourselves is, what's the thermal performance of a lightweight aggregate block in its wet state? And that we don't know. So why is it so important then to use Quinn Lite blocks at our key junctions and to detail the junction correctly so that the Quinn Lite block is kept dry? A recent thermal bridging study carried out on 17 key junctions compared the psi values across that junction between Quinn Lite, dense blocks and lightweight aggregate blocks. Dense blocks, self-explanatory, are standard masonry units. Lightweight aggregate blocks are a thermal block and they're manufactured using lightweight aggregates. It's important to note that the Quinn Lite block outperformed both these other blocks in all of the 17 key junctions. Compared to the dense block, the Quinn Lite block performed up to 750% better across the key junction. When compared to the lightweight aggregate block, the Quinn Lite block performed up to 200% better across the key junctions. So if we look at these figures, it's a no-brainer that a Quinn Lite block should be used to get the best thermal performance across our key junctions. So we've looked at two typical details and looked at how the Quinn Lite block can easily be kept dry to get or maximise its thermal performance. A full range of details are available in our accredited construction details on our website. In addition, our technical team are on hand to work with you to develop any additional details that may not be available currently.